Discrete Math Introduction to Proof. First off, what is a proof? So what is a proof? A proof is an argument that demonstrates why a conclusion is true. If you recall, an argument basically is a sequence of premises that basically implies a certain conclusion. So this argument basically is ANDed together and then with the implication towards the final statement, which will be the conclusion. So what is a mathematical proof? Mathematical proof is basically a mathematical argument that demonstrates why a mathematical statement is true. So these are the basic methods of a proof. We have direct proof, proof by contraposition, trivial and vacuous proofs. You have contradiction, equivalence, and mathematical induction. So let's start. What is a direct proof? Direct proof, we are making use of the conditional statement P implying Q. So we will assume that the first statement, the antecedent or the hypothesis, is true. Then we are going to use the definitions and previous proven theorems to show that the conclusion must also be true. So if you are going to summarize this has two steps. So first step is you're going to assume hypothesis is true. And in the second step, we're going to show or illustrate that the consequent or the conclusion must also be true. So the implication here, the inherent, the hidden directive is we're going to use one, the assumption for us to be able to show that the conclusion must also be true. So let's give an example. So give a direct proof that if n is an odd integer, then n squared is odd. So let's rewrite this. So if n is an odd integer, then n squared is also an odd integer. So given that problem, we can now go to the direct proof. So assuming that the hypothesis is true, we have to show that the conclusion must also be true. So if n is odd, then we could therefore let n to be a certain twice of a certain integer plus 1. And this is the definition of an odd number. So where k is an integer. Now, with this assumption, we can now proceed with showing that the conclusion is true. So the conclusion is n squared is odd. So is it true? We cannot assume it, but we have already an initial assumption that n is an odd integer. So we will build the argument from that so that we could come up with an argument that is true and true and true and so on. So this will imply the conclusion should be true as well. So given this in mind, we are going to start with the truth. So we know and we assume that n is twice of k plus 1. So this is already truth by assumption. Therefore, we could manipulate this using algebra now. So with algebraic laws, we could establish more truth or manipulate this equation. So one manipulation is if you square both sides, then it will still be equal. So this will be n squared is equals to, so twice of k plus 1 squared. So we have 4k squared plus 4k plus 1. Now, let's remember that the goal is to show whether n squared is an odd integer. So is 4k squared plus 4k plus 1 odd? We cannot tell. Basically, it's wrong to assume that if we substitute a certain particular value, then we are going to prove this theorem. So for example, if I substitute 1 for k, then this will be 4 plus 4 plus 1 is equals to 9, and that is an odd integer. Yes, that is an odd integer, but it's not a proof. It's merely an instance of this equation. So for us to end up with a proof, we have to appeal to the definition. And we know that an odd integer is defined as 2k plus 1. So if we could somehow produce a pattern like this, then we could now argue that by definition, n squared is also an odd integer. And that pattern can easily be done by letting, or we could factor this 2, and you have 2k squared plus 2k, quantity plus 1. So what we did here is merely to factor out the 2 so that it will look like the odd number definition. So if we examine this, it looks like twice of this plus 1. So if we let, for example, if we let m be 2k plus 2k squared plus 2k, then this will be equals to 2m So this will be 2m, so equals 2m plus 1, where m is of course an integer. That is by closure property. You have 2 times an integer plus another integer. By closure, that is also an integer. So with this pattern now, 2m plus 1, therefore we can conclude that this is an odd number. So therefore it's an odd number. And that's the direct proof for this. Because n squared also ends up in a pattern 2m plus 1, where m is also an integer. Okay. Next off, we also have proof by contraposition. As what we have shown already, the implication is equivalent to its contrapositive, not Q implying not P. Therefore, with this logical equivalence in mind, we could basically compute or convert the statement into its contrapositive and then apply direct proof. So that will be proof by contraposition. So you could think of it as an application of the contrapositive plus the direct proof. So we take the negation of Q as the hypothesis, and using the definitions and previously proven theorems, we show that not of P must follow to be true. So as an example, prove that if n is an integer, then and 3n plus 2 is odd, then n squared is odd. So I could write this as if 3n plus 2 is odd, then n is also odd. And we could try to prove this by direct proof. However, we will encounter a certain problem. For example, so in the first step, we are going to assume that the hypothesis is true. So that means 3n plus 2 is an odd number. So after that, we could show that Q must also be true. By the way, I'm using direct proof here just to show that sometimes there's a limitation with the method. Because if I'm going to solve for n now to show that n is odd by starting with the assumption, so it will be now 3n plus 2 is equals to 2k plus 1, which is the initial truth. So subtract 2 both sides, and I will end up with 3n equals 2k minus 1. And the problem sets in because to solve for n, I have to divide both sides with 3. And the problem with this is 2 over 3 is no longer an integer. So k must be divisible by 3 for this number to be a whole number. So the problem now is we end up with n being not an integer anymore. So it's a limitation for our direct method. So with this we could try the contraposition. So contraposition, first we're going to compute the contrapositive and then come up with the direct method. So for now we could start with its contrapositive. So this is equivalent to if 3n plus 2, or contrapositive will start with the conclusion, negation of the conclusion. So if n is even or not odd, okay, then 3n plus 2 is also even. So after computing its contrapositive, we can now proceed with the direct proof. So this is now first you have to assume okay, the hypothesis is true. So in that case, I'm going to assume that n is twice of a certain k, where k is an integer. Then the second step, we're going to show that the conclusion must also be true. So to avoid confusion, by the way, this is no longer P if you will still consider this original statement as P. And if this conclusion is Q, since we are already now using the contrapositive, this statement is already the NAT of Q, and this statement is the NAT of P. So somehow it might be safer to say that this is just the hypothesis. Assume hypothesis is true, and then for the second one, show that the conclusion must also be true, because the hypothesis now is NAT of Q, and then the conclusion is the NAT of P. So if we're going to show that 3n plus 2 is even, we could start with this n is equals to 2k. This is now true. So if we're going to substitute, so this is now 3. So substitute the assumption to the second statement. So 3 times twice of k plus 2. Okay, simplify. So we have 6k plus 2. So is this an even number? Right now we cannot tell. Even if you substitute any number there, like 3, 6 times 3 you have 18, plus 2 you have 20. But the idea is, yeah, it's even, but still it's not a proof. Again, you have to appeal to the definition. So definition of an even is twice of any integer. So we could factor this out by factor that out first. So twice of 3k plus 1. And in that case, we could now let m, or any variable, to be equals to 3k plus 1. So therefore this will end up into twice of m. So twice of m is the expression that we arrive when we manipulate the original 3n plus 2. So with this twice of m expression, we can tell that this 3n plus 2 is an even number. So that's it. Now we'll have an exercise. So prove that if n is equals to a times b, where a and b are both positive integers, then a is less than or equals to square root of n, or b is less than or equals to square root of n. We're going to solve this in the next video.